So the topic of the day is going to be symmetries, and we're going to discuss two primary symmetries, one being point symmetry and the other being line symmetry. If we've got a line symmetry, as shown in this diagram down here, what happens is basically that line of symmetry is a perpendicular bisector of two different points on the curve. So as you can see right here, if I have this point symmetric to this point over the line, then that dotted line is the perpendicular bisector of the segment joining those 2 points, and you can see that throughout this figure. If I've got a point symmetry, then it ends up that if I reflect this dot here over that point, it ends up on this dot, or likewise this little X mark here over that point, it lines up on this part of the curve here. Then the segment connecting those 2 points has this point of symmetry as its midpoint. So that's kind of the properties of the two types of symmetries. Now, again, we can see a couple of different symmetries that we're going to test for today. We're going to look at an x-axis symmetry. So that's where your x-axis is that line that takes and has a perpendicular bisector to any 2 points on the curve. Y-axis symmetry and an origin symmetry. Now, you'll notice that when I have an x-axis symmetry, that the x-coordinate remains the same, but the y-coordinate is actually opposite. When I have a y-axis symmetry, you'll notice that the y-coordinate is the same, but the x-coordinate is the opposite. And in an origin symmetry, that's the point we're going to look at. So the origin, we recall, is just the point 0, 0. If I were to take this point here and flip it over to this point here, we notice that both the x's and the y's are now opposites. So the test for each of these symmetries is as follows. We know that, as we stated before, the y's are opposite in an x-axis symmetry. So if I were to plug in x and y and x and negative y to a curve, in other words, substituting negative y for y, the resulting equation is going to remain the same. Likewise, if I have y-axis symmetry and I plug in negative x for x, the resulting equation is going to be the same. And finally, if I have an origin symmetry, then I plug in negative x and negative y for x and y, and the resulting equation is the same. Let's do a couple of applications to just kind of clear all this verbiage up. So what I want to do is I want to see if I have origin symmetry in these two equations. So what I'm going to do is I'm going to make a substitution of negative x for x and negative y for y and hope that I get this equation back. So for y, I plug in a negative y. For x, I plug in a negative x. And then I'm going to take and simplify this entire equation. So I have negative y. When I cube a negative x, I end up with a negative x. So what I have is I have a negative 3 times a negative x cubed is a positive 3x cubed. When I have a negative x times 5, I just have a negative x. So now I want it to look exactly like this. Right now it's a little bit different. So what I'm going to do is divide both sides by a negative 1, which leaves me with y equals negative 3x cubed plus 5x. And you'll notice that the resulting equation, after plugging in and making a substitution of negative x, negative y, is exactly the same as the original. So yes, this is origin symmetric. Now if I do the same over here and plug in a negative y for y and plug in a negative x for x, you'll notice negative x to the 6th power is a positive x to the 6th, and that equals negative y. But again, I want to make it look exactly like this, so I'm going to divide by negative 1 and I get y equals negative x to the 6th. And in this case, this negative in front of the x to the 6th is not present in the original. So this is not origin symmetric. So let's do the same but test for x-axis and y-axis symmetries. And we'll start with x-axis. So again, what is the test for x-axis? Well, if this is my x-axis and I have a point here and I'm flipping over and getting to a point here, the x's are the same, but the y's are opposite. So that's the substitution I'm going to make. So I have x squared plus negative y is equal to 8. And you'll notice that's x squared minus y equals 8, which is not the same as the original. So this is not x-axis symmetric. If I want to test for y-axis symmetry, again, I take a look at my x and y axis and I put a point over here and I reflect that over the y axis, and I notice my x coordinates are opposite, but my y coordinates are the same. So that's the check that I want to make, and I'll substitute a negative x in for x, a y in for y, and hope that I get my same initial equation back. Negative x squared is just x squared plus y equals 8. And you'll notice that's the exact same as the original equation. So yes, this is y-axis symmetric. Again, let's do some more practice. We'll find out if this is x-axis symmetry. So if it's x-axis symmetry, we know the y's are opposite. Make our substitution. So I have x minus 2 quantity squared plus opposite of y squared is 1. You notice in this case that this is the same exact term. In this case, negative y quantity squared is just positive y squared equals 1. Same as the original, so yes, this is x-axis symmetric. Now we're going to check for y-axis symmetry. In order to do that, once again, we know that x is the opposite and y remains the same. So I'll make my substitutions. That's negative x minus 2 quantity squared plus y squared equals 1. This I'm going to take and FOIL out to see if it's the exact same. I'm not sure it's going to be, but we'll check. So if I FOIL that, we end up with x squared. There's a positive 2x and a positive 2x, which is positive 4x plus 4 plus y squared is going to equal 1. Now the question is that the same as this quantity here? Well, let's find out. If I were to take x minus 2, square that, add y squared to it, x minus 2 quantity squared is x squared minus 4x plus 4 plus that y squared is going to equal 1. So you'll notice that's negative 4x, that's positive 4x. These are different. So no, that's not going to be y-axis symmetric. So all I've really got in this case is x-axis symmetry. Next, we're going to take an actual graph and regraph it so that it becomes origin symmetric. And we talked about earlier that if we have origin symmetry, and I put one point over here, xy, and flip that point over the origin, it ends up in this quadrant, which has a correspondence of negative x and negative y. So basically what I need to do is I need to draw a new figure such that each of these points are redrawn so that their opposites appear. So in this case, I have the point 1, 2, 3, 4, 5, 6, 1. In this case, that's 3, 4. And over here, I have 1, 2, 3, 4, 5, negative 5, 2. So now what I'm going to do is take all the opposites of these. So the opposites of 6 and 1 are negative 6 and negative 1. The opposites of 3 and 4 are negative 3 and negative 4. And the opposites of negative 5 and 2 are positive 5 and negative 2. And you see, after connecting those dots, I have a figure that looks exactly the same as my original. It's just been reflected over the origin. A little more practice finding intercepts. We're going to find the x and the y intercept, and as we discussed, I believe it was yesterday, to find your x-intercept, set y equal to 0. So I'm going to do that, and I get 0 is equal to 6x squared plus 19x plus 10 over x squared minus 9. I need to solve for x in this case. If I multiply by x squared minus 9 to both sides, I just get 0 equals 6x squared plus 19x plus 10. All right, and I'm going to take this opportunity to show you a different way to maybe factor this equation right here, because that's what we're going to have to do in order to solve it. You could go old school and do the quadratic formula, but no need. I'm going to use what's called a 5-step method. And in a 5-step method, I multiply my a term times my c term, and I get x squared plus 19x plus 60. And then I'm going to take and factor this. So I have an x here, 15 and 4 get me to 60 and add me to 19. But you'll notice this is not multiplied back into 6x squared plus 19x plus 10. So what I'm going to do is I'm going to take and divide each of these terms by 6, which was my initial a term, reduce, which gives me 3 goes into each of these, 5 here, 2 here, and 2 goes into each of the next guys, 2 and 3. Then I'm going to bring my denominators that are left over to the front. And that gets me a 2x plus 5 and a 3x plus 2. And you'll notice that in this case, if I FOIL that back out, I will get my original. So I call that a 5-step method in order to factor the quadratic when I've got some a term in front. When solving this, I basically have negative 5 halves is equal to x and negative 2/3 is equal to x. So those are my x-intercepts. Now if I want to go back and find my y-intercepts, this is actually a lot easier in this case. To find my y-intercept, I'll just take and set my x equal to 0. So you'll see a whole bunch of stuff goes away. So this is 6 times 0 plus 19 times 0 plus 10 over 0 minus 9, and we end up with negative 10/9 for my y-intercept. And it's as simple as that for any kind of function. Granted, factoring may be a little more difficult, but to find your intercepts, set x or y equal to 0. That's all we've got today. Fill out the summary form, go to my math lab, get the problems done. We'll see you tomorrow.